Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video, we're going to look in more detail about how numbers are stored and manipulated on the computer, and in particular how Scala deals with them. In the last videos, we've looked at how there are some numeric types and we can type in numbers and how we can do operations on them. And we saw how we can call methods to do conversions between things. If you did a lot of playing around with that, you might have noticed that there are some things that come out kind of funny. So, for example, if we bring up Scala, maybe you never did anything like this, but if you take the number 2 billion, and you add 34 to it, you get a result that you would expect. But what happens if you add another billion to it? That's definitely not what you expected. Okay? Even small children often like to show their prowess at math by adding things like 2 billion and 1 billion and tell you that it's 3 billion. They would know that is not the right answer. And so the question is, well, what happened? What went wrong? Why did that give us the wrong answer? And to understand the answer to that question, you have to know a little bit more about how numbers are being represented inside of the computer. So we use, for our normal dealing with numbers, we use the decimal system. So for example, the number 365 is 5 ones plus 6 tens plus 3 hundreds. So at some point in your early education, you had to write things out in this longer format. And the things that you're multiplying here are different powers of 10. So this is 10 to the 0, 10 to the 1, 10 to the 2. If there were a thousands digit, it would be 10 to the 3, 10 to the 4, 10 to the 5, etc. There's nothing particularly special about the decimal system. There's nothing special about using 10 as the base for your numbers. You can use anything that you want. 10 just happens to relate nicely to the number of fingers that we have. But there really isn't anything else that's particularly special about it. When you go about building a digital computer, you have to represent numbers as currents on wires. It's currents or voltages on a wire. And so the turns out that representing 10 different levels is hard from an engineering standpoint. It's much easier to just represent 2 levels. So instead of having 10 options like we do in decimal, where you can have digits 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, computers represent things in binary. There are only 2 possibilities. Either it is on or it is off. Okay, so the off is 0 and the on is 1, and those are the only possible digits that you have. And that's the way that the computer is doing things inside. Now, of course, as you can see here, it prints it out nicely for you as decimal, but for understanding why an error like this occurs, you really have to have at least some understanding of what's going on inside of the binary. So we're going to take a little bit of time to talk about that. So how do we get binary numbers? Okay, so if I were to type in a reasonably long number, such as that, in binary, what would the value of this be? Well, just like in decimal, this is the ones digit. This is now the twos digit, though. It's 2 to the power of 1. This is the fours digit, next to the 2 to the power of 2. 8, 16, 32, 64, 128, 256, 512. So this 1 here is basically represents 512 going into the value. This represents a 64 going into it. This is 16, 4, and 2. And you can add those all up And so we said, now of course that it interprets that as a decimal number. So we said 512 plus 64 plus 16 plus 4 plus 2, and that happens to be the number 598. Now, if you are working inside of Scala, there happens to be a method on integers called toBinaryString, which will print back out the binary value, and you can see that indeed 598 is this, which happens to be what we started with originally. How could you do that on your own? Okay, well, the way that you do this is to do repeated division by 2, and you can think of it as a modulo operation or doing a check for whether the number is even or odd. So if we start with 598 here, well, 598 is an even number. So if you do 598 modulo 2, which is to get the remainder after division by 2, you get 0. That 0 means that there is a 0 here in the binary representation. To get the next digit, you would divide by 2, and then take that answer and do modulo by 2. So check whether it's even or odd. That modulo by 2 is just an even or odd check. This number happens to be odd, and so you get a 1. That 1 is the 1 right there. And then you take the 299 and you divide by 2 again. Now remember, this is integer division, so you're only taking the quotient. You're throwing away the remainder. Actually, that remainder there wound up being written up in here. This gives us 149. 149 is, of course, odd, so we have another 1. So we found 0, 1, 1 from that modulo, and that modulo. And we would repeat this. 149 divided by 2 is 74, which is even, so we would get a 0 there. 74 divided by 2 is 37. The 37 is odd, so that gives us the next 1. And you can repeat this until you get to the value 1, and then you just write that down. And that gives you your answer. So that is one way of converting from a decimal number into binary. The book talks about another way as well. This one is my preferred method, as I think it's a little bit less error prone. So how can we do mathematical operations on binary numbers? We can open a VI session here, and I'm going to come up with 2 binary numbers, and I'm going to actually make these 8 bits. And so when they're smaller than 8 bits, I'm going to have some leading zeros on there. Okay, so there's one binary number, and there is another binary number. Now, what are these numbers? Well, this is 1 plus 4 plus 8 plus 32. 1 plus 4 plus 8 plus 32. So the top number is 45, and the bottom number is 1 plus 2 plus 8 plus 64. 1 plus 2 plus 8 plus 64 gives me 75. The sum of those two would be 120, which we should be able to convert to binary. But before we do that, let's see how we would add these together. Now, the thing about, in fact, I'm going to insert an extra line here. Turns out that in many ways, if you start playing with addition or multiplication in binary, you almost wish you could go back to 3rd and 4th grade and say, oh my gosh, I don't want to do decimal, I want to do binary. Because in 3rd and 4th grade, or even earlier, when you were learning, for example, addition tables and multiplication tables and such, in decimal, your multiplication table needs to have at least 100 entries in it. So you have a column for 0 through 9 and a row for 0 through 9, and there are 100 entries in that table. The binary version is a lot smaller. It's 2 by 2, so there are only 4 entries, and that's true for whether you're doing addition or whether you're doing multiplication. But there are some nuances to this. So for example, 1 plus 1, well, we normally say the answer to that is 2, but we have to write this in binary. I can't write 2 in binary. When I write 2 in binary, it is 1, 0. Okay, well, you know what you would have to do normally if you came across this in math. If the number added up to 10, you would only write down the 0, and you would carry a 1. And that's exactly what we're going to do here. 1 plus 0 plus 1 is 2. So we get a 0, and we carry a 1. 1 plus 1 plus 0 is a 0, and I carry a 1. 1 plus 1 plus 1, well, that gives us 3. 3 is represented in binary as 1, 1, so a 1 goes there, and a 1 gets carried. 1 plus 0 is 1. There was no carry, so 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. And so that is what we get when we do this addition. Should be 1, 1, 1, 1, followed by 3 zeros. The 2 binary string is not going to print the leading 0. So there you can see we were able to do this correctly. So the only difference really is, in many ways, the addition is much simpler, but you do a lot more carrying because a lot of the things that you add will wind up adding to a number greater than 1. Anything greater than 1 has to involve a carry. The book covers multiplication. I'm not going to do that in the video. I did the addition because it winds up being very significant for another, for the explanation of this error that we had before. Why does that go negative? Well, in some ways, to answer this question, you have to know what a negative number is in Scala. And so the question is, well, how would we represent negative numbers? So you might remember that, mathematically, what does it mean for if you have the value negative 67? Okay, what does that mean mathematically? If I give you a number x, what does it mean for something to be the negative of x? Well, we often use the term negative here, but in reality this should be read as the additive inverse, because the real mathematical meaning here is that if you take x and you add it to its negation, its additive inverse, you always get 0. And so it turns out that in computers, things are wired so that this mathematical property holds true, and it has a significant advantage to it in that subtraction winds up being implemented with the same set of wiring that addition is. The math works nicely there. And so that leads to the interesting question of, okay, well, how would I get an inverse for a binary number like this? I need to find something that I could add into here such that after I add everything, I get all zeros. Well, of course, the answer is, well, nothing. There is nothing I could put there because I'm not allowed to put a minus sign. That's not something that I can have. All I get are 1s and 0s inside of the computer. The trick to this is the fact that when you're storing these values in a computer, you're limited to a certain number of digits. Okay, so imagine if you were in a math class and your teacher gave you the really weird rule that you're only allowed to use 3 digits for your numbers. So, for example, the number 365 is a perfectly happy number, as is the number 804. Okay. But now what's going to happen if we add these together in a system where all that we can represent are 3 digits? Well, the 4 plus the 5 gives you a 9. We get a 6. We get a 1, and there was supposed to be a carry of a 1, but if you're only allowed to keep 3 digits, that last number gets lopped off. Okay? And that's exactly what is going to happen here. All of the numbers that we're storing have a certain finite precision to them. In the case of an int is allowed to store 32 of binary digits in it. It has 32 what we refer to as bits in it. There are other numeric types we'll talk about in just a second. The smallest one is actually what I have written here. It is 8 bits, and we call that a byte. And that's a very standard term across computing. 8 bits gives you a byte, and since I don't feel like writing out 32 digits here, I'm typically going to work with those with 8 bits. So if I were doing this in a byte, the thing is, if my sum adds up to 1 followed by 8 zeros, this 1 will be thrown away, and I will be left with just the 8 zeros. And so now this is a problem that we can solve. Nothing would have actually given us all zeros, but we can find something that we can put in here for the question marks, and it will give us a 1 followed by 8 zeros, and then that 1 gets thrown away so that our result is still a 0. So what do we add to 0 to get 0? Well, 0. What do we add to 1 to get 0? Well, if we add a 1, we're also going to carry a 1. And now we have a 1 and a 1, and that needs to be a 0. And we've carried a 1 here, and we have a 1 and a 0, so we have to add in a 1, and we carry a 1. And we have to add in a 0, and we carry a 1. And we have to add in a 0, and we carry a 1. And we have to add in a 1, and we carry a 1, and we have to add in a 1. Okay, so the additive inverse of this number here, this was 2 plus 4 plus 16 plus 32, 2 plus 4 plus 16 plus 32, is that, and we can check that 54 is indeed the binary string 110110, which is what we have here. Remember, it doesn't print the leading zeros. And I'm making the argument that this is the representation for negative 54. So if we take negative 54 and we convert it to a binary string, you'll notice, well, it starts off 0101, 0101, 0011. Those are the lowest 8 bits here, the things that we found. But this has a whole bunch of 1s going on up, and you can see, and that's because the negative 54 is an int. This isn't printing just 8 digits, this is printing 32 digits because the int stores 32 digits. So it turns out that any number that starts with a 1 in the highest bit, so if it were a byte, it would be in that 8th top bit. If it's an int, it's up in the 32nd top bit. If you have a 1 here, the number is seen as a negative number. And these are the signed values. So int is signed in Scala, as are the other numeric types with the exception of char. Char is actually an unsigned value. So whether this is 1 at the top or not, it will still see it as a positive value if you're dealing with a char. So, but the negative numbers are just what you would get if you keep the rule that when you add them together you get zeros, because once again that gets thrown away. And so your result here is 0. There is an easier way to calculate this. Okay, so it's a 2-step process. The first step in the process is to flip all the bits. And then the second step in the process is to take that value and add 1 to it. So if I add 1 to that, well, I get a 0 and I carry a 1. This becomes a 1. And then everything else stays the same. And you'll notice that this number here is the same as this number here. So the easy way to get, and this form of representing negative numbers is called 2's complement. in the early days of computing, people played with other ways of representing negative numbers, but the 2's complement 1 out because it does allow you to have a single set of wires that does addition and subtraction, because you've preserved the mathematical definition of what it means to be negative and, in a sense, what it means to do subtraction. You can always do it this long way to prove to yourself that you're doing the right thing, but you can also do it this short way where you flip all of the bits and then you add in 1 to get the final answer. So I mentioned that an int is 32 bits. You can actually ask the int how big and how small it can get. So it turns out that the biggest number you can represent in the 31 bits that you have, remember this top bit winds up being telling you that you're negative, the biggest number you can represent below that is this. It's a little over 2 billion. And if you go over that, so for example, if you take that max value and you add 1 to it, you actually wrap around and you get the minimum value. And that is why when we added this up, this went to 3 billion, which is bigger than the maximum that an int can represent, and so it wrapped around to negative. If you need bigger numbers than that, there is a different type called a long. And you can represent long literals just by putting an L. It can actually be lowercase or capital. I will generally use a capital because the lowercase looks too much like the number 1. And if you just put that L after your literal, you get a long. The long doesn't use 32 bits, it uses 64 bits, and so that gives it a much larger range. I won't even try pronouncing what that number is, but clearly it is very, very large. And so you can use longs if you need to, because you need additional digits. There won't be many things in this book where we do. Every so often we'll play some fun little math games where it's nice to have bigger numbers, and we might use them. There are also some applications where you don't need as many bits. You don't need really big numbers, in which case you could potentially save memory by using other types, like the short is only 16 bits, and so it only goes up to a little over 32,000. And then there is also the byte type, which is the 8-bit values that we've been playing with over here, and it can only go up to 127, and as you'll notice, the min value is negative and with a 1 greater magnitude. So negative 128 and positive 127. So those are the different integer types that you have. We've talked about double. It turns out that doubles have a range on them too. You can only go so far with doubles, though that how far you can go is very large, and it has a minimum. The double uses 64 bits, and I won't go into the details of how it represents a number using those 64 bits, but it winds up being kind of like scientific notation in binary. The double also has a finite number of digits, and this can lead to some very interesting behavior. For example, 1 minus 0.9 minus 0.1, you would normally expect that to be 0. But it's not, because it turns out that 1 minus 0.9 gives you something that's not exactly equal to 0.1, because it's kind of like representing the fraction 1/3 in decimal. Well, that's equal to 0.3333333 repeating. Well, but if you have to cut it off at a certain number of digits, in math you can write ... If you have to cut it off, though, you get something that is technically not 1/3. It's a little bit different. Same thing happens here. It turns out that 0.1 is not perfectly represented in binary. It would need an infinite number of bits that are repeating. And so when you do this math, you get something that's not quite 0.1. And so you can have some weird stuff happen there. There is another type for storing these non-integer values. It's called a float. The float is actually smaller than a double. It's only 32 bits. Once again, there are some applications that like to use that. And so it can store a smaller range of numeric values. By default in Scala, most things wind up becoming ints and doubles. And for that reason, we will utilize primarily ints and doubles for our numeric usage. But you should be aware that these other types exist and that they have other bounds, particularly for if you need larger numbers, you can use something like the long. So that's it for this lecture, and we'll see you soon.